Of you. First, I would like to thank the Indo-US Forum for Science and Technology Foundation, Science and Technology Forum, and the organizers of this workshop, particularly Mahesh and Sujit, for giving me this opportunity. In this presentation, I will be trying to highlight some of the recent trends in atomization and spray formation in gas turbine combustors. Much of my own understanding of this field came through the research that we have been doing in our group for the last 6-7 years, funded by Indian Space Research Organization. Dr. Tarakan is here, and GTRE. And I would also like to thank my colleagues and students involved in the project. One of them, Professor Datta, is already here. So as we all know that atomizers have a large, have a wide range of requirements, and so to design them, you need to satisfy a lot of parameters. So in here I would not go into all those details, but there have been a lot of studies in the literature where the performance of a combustor, impact of atomization on combustor performance has been studied. We can see that parameters like mean drop diameter and spray cone angle can significantly affect parameters like combustion efficiency and pattern factor. Also, the ignition energy is also significantly affected by the drop size. But in today's context, what is probably more important is the fact that emission of pollutants like soot, NO, CO, and unburnt hydrocarbons can also be significantly affected by the drop size in the spray. Another impact of atomization, which is less often discussed, is that the combustion instability can also be significantly affected by droplet initial diameters. So with all these things, when we are to get a good combustion, we obviously need a good atomization. That is why this whole workshop is all about, I believe. So as we know, the two major types of atomizers are pressure swirl atomizers, which has its advantages like good mechanical reliability and an ability to sustain combustion at very low mixture strengths, but its limitations are soot formation and potential plugging of the orifice. On the other hand, air blast atomizers have the advantage of low soot formation, and the fact that the outlet temperature distribution is primarily governed by the air flow. The changes in fuel flow do not significantly affect that, so pattern factor is less affected. But it has very poor atomization quality at startup, and it is prone to thermoacoustic instabilities. So, since these two common types of injectors do not satisfy all the requirements of a modern gas turbine combustor, people had to look for new types of combustor, and the most intuitive, new types of atomizers. The most intuitive one being so-called hybrid atomizer, which tends to put in the best of both the worlds. So in one such design, which is the piloted air blast, it combines a pre-filming air blast atomizer with a simplex pressure swirl nozzle at the center. At the startup or low fuel flow rate, most of the fuel is supplied through this pilot nozzle, so that the characteristics are similar to that of pressure swirl atomizer. Whereas at high, as the fuel flow rate increases, fuel is supplied to both the streams, and at high pressure, at high flow rates, most of the fuel goes through the air blast injector only. So we get good atomization at low flow from the pressure soil part, and similarly improved lean blowout limit. But at high fuel flow rate, since it is predominantly like a air blast atomizer, it gives a low soot formation. A simpler version of hybrid atomizer is the air blast simplex, where all the fuel, unlike the previous case, is supplied through the simplex nozzle. Here what has been found is that an increase in air flow rate helps in always helps in atomization, but increase in fuel flow rate can help or hinder the atomization depending on how it affects the relative velocity. Another innovative kind of atomizer is what Professor Raghunandan discussed at length, is the effervescent atomizer, which works on quite a different principle in that here the liquid is not made into a thin, we don't get a thin film of liquid, instead it's the bubble of gas or air which shatters the liquid at the injector exit. So here the major advantage is that we get a good atomization with even with low injection pressures and air flow rates. But it also the aeration of the spray reduces the soot and smoke formation, but it also has its limitations. So, as we go for these improved varieties of injectors, what we find is that there are too many parameters affecting their performance. And so if we want to design these kind of injectors, we have to play around with too many parameters. So if we stick to the I mean, if we want to do experiments with all of them, that will become a very costly proposition, at least especially at the design stage. So a much cheaper alternative is provided by CFD, especially with the availability of more powerful computers. Even laptops can solve so many of the important problems these days. So what is needed at this stage is to have comprehensive predictive models which will have minimum dependence on empiricism at the design stage. Of course, experiments are necessary, and I will discuss about that also, but there will be, I mean, more modeling with limited amount of experimentation, mainly to improve the model that can be useful, and particularly these models can be very useful for high temperature and high pressure situations where experimentation is extremely difficult and costly. So the major steps, this is how in most of the comprehensive models that are there in literature, this is how they conceptualize the spray formation process. The liquid sheet that comes out of the nozzle breaks up first into ligaments and then into droplets, and the comprehensive model should have these three elements. First is the modeling of the internal hydrodynamics, where you get the inputs from the inputs of injector geometry and flow conditions, and you as output you get the parameters like liquid sheet thickness, liquid sheet velocity, cone angle, and these things then are fed to the sheet breakup model to obtain breakup length and mean droplet diameter. And using these using these inputs again, if you there is a stochastic part of the comprehensive model which can give you some idea about size and velocity distribution. Unfortunately, as far as I know, there is no comprehensive model which encompasses all these three elements. There has been quite a number of works involving the first two. Milind Jogis here, they have done quite a lot on this, and there has also been some amount of work on using the last two. I mean, very recently we did some work using planar sprays. It was funded by ISRO, and we are also continuing now for gas turbine sprays in a similar thing. So coming to the first part of it, the internal hydrodynamics of injector, this is probably the most well established part of the three submodules. Nowadays one looks at the detailed flow field of the two-phase flow using approaches like VOF, although some people use techniques like arbitrary Lagrangian Eulerian. There have also been some work where less detailed models have been done focusing on more on the velocity, mostly on the velocity profiles, and also some work on semi-empirical models combining experiments with the numerical models. But these detailed simulations have mostly been limited to pressure swirl atomizers. But these models can be very useful, like this work on pressure swirl atomizer shows. I mean, you can use these use this model to investigate the effect of varying the design parameters both on in the details of the local flow field as well as on global performance parameters like liquid sheet thickness, discharge coefficient, etc. But they need to be verified and these models need to be verified and fine-tuned with the help of experiments, which can be both flow visualization experiments and PIV studies for investigating the details of flow fields and phase boundaries, and also validating the detailed the performance parameters, the outputs of the like film thickness, spray cone angle and discharge coefficients, which are directly useful. In our group also we have been doing, we are trying to do similar work on a design of hybrid atomizer. The details are put up on the poster outside. Here we are trying to look at features like providing recesses, which Professor Raghunandan also mentioned. In fact, when he was showing this slide, our student Shovik was sitting over there. I could see him looking and smiling because he thought he was doing something very innovative. But when it comes to effervescent atomizer, there very little amount of work has been done on the modeling of the internal hydrodynamics. These results are by a paper by Professor Raghunandan and Professor Ramurthy, which Professor Raghunandan just now mentioned, and the flow visualizations are also from the same work. In fact, quite a lot of flow visualization studies have been done, but still a lot more needs to be done on the modeling issue. In fact, in the most comprehensive review paper by Professor Soika, this has been listed as one of the areas in which more work is needed. Now we coming to the second part of it, that is the breakup of liquid sheet. This is probably the most controversial area of the controversial part of the submodule. Here what is normally done, people use some idealized configuration like a planar sheet or a cylindrical axisymmetric sheet, and very rarely a conical sheet to represent the liquid sheet coming out of a gas turbine injector. And the common approaches followed are people mostly rely on the linear stability analysis, although there has been significant amount of work on nonlinear stability analysis. Also there have been a lot of numerical simulations, both simplified numerical simulations where some kind of reduced order models have been done by reducing by lumping in one dimension or things like that, and of late there are some very detailed numerical simulations. But the major problem here is that several alternative mechanisms are possible depending on the conditions, and there is quite a bit of lack of consensus on the mode of sheet breakup. I would like to share with you one of our very recent experience. We had sent out a paper to Atomization and Sprays, and one of the reviewers, he was extremely dissatisfied with the breakup mechanism that we adopted, but finally we could see some other people who had also adopted a similar approach, and probably that got the paper through. But definitely a lot more work needs to be done in this area. So in the linear stability analysis, the information that comes out from the studies are mostly the maximum growth rate and the critical wave number that produces the maximum growth rate. Generally, a temporal stability analysis is done because that is easier to do. The most unstable wave number that gives us an idea about the droplet size, whereas the breakup time, which translates to breakup length, is obtained from the information on growth rate and the amplitude ratio of the amplitude of disturbance at breakup to that at the initiation. While this in a linear analysis, this maximum growth rate is easily obtained, but to get this amplitude ratio from a linear analysis, people take recourse to various ways. Like many people use, even for non-planar sheets like axisymmetric sheets, many people use the relation for planar sheets. There has been some work where they have assumed the amplitude at the instant of breakup to be equal to the mean radius of the liquid sheet, but probably a more sophisticated approach would be to combine this linear stability analysis with experiments and directly determine the amplitude ratio at breakup from the experiments, as has also been recently done. But this shortcoming can be overcome if we go to nonlinear stability analysis. As we know, the breakup mode of disturbance can be both sinus or varicose or even a combination of the two. And although it is particularly from the linear stability analysis, it is generally believed that the sinus mode will always dominate. Many of the nonlinear studies, including that by one of our own recent studies, have shown that depending on the parameters, there can be situations where both the sinus or the varicose modes can dominate. And these kind of nonlinear studies can also have also led to good agreement with experiment, but again here there is a catch. Thing is that these results predicted by this nonlinear stability analysis is strongly dependent on this initial disturbance parameter, initial amplitude of the disturbance eta 0, which is, but that is something very difficult to measure from in an actual experimental situation. I mean, unless it's a very controlled experiment, the any kind of disturbance may come up, and it is difficult to say with confidence that this was the exact disturbance that was there. So often it may end up that you will get some amplitude ratios, some initial amplitude, which will give you a good agreement with experiments. But what most people do, I believe, I mean, including we also did the same thing, that make sure that the disturbance amplitude that we are taking is within the normally accepted range, or normally the range that is normally encountered. So, we can also get very complicated axisymmetric and non-axisymmetric flow patterns from a nonlinear stability analysis. These are the results by Milind Job. Other than using this nonlinear stability analysis, people have also used discrete vortex method to for doing the same thing, that is getting sheet breakup profiles, and it is possible to get both axisymmetric and non-axisymmetric modes here. And in most of the studies, it is assumed that the sheet breaks up in a longitudinal manner, and there has been using that model, there has been quite a number of studies which shows excellent agreements with experiment, as this very recent study also shows. But but some high speed visualization studies show that there can be other modes of breakup like cellular mode. So, so far as modeling is concerned, much more work is needed to to ascertain the breakup mechanism. This high speed visualization is one way of ascertaining that. And the other way is of course to go for very detailed numerical simulations like these DNS results show. I mean, with this kind of detailed simulation, it is it is possible to get idea about both the flow field as well as the sheet or jet breakup profile. There has been some studies using boundary element methods also, and in these studies they have used simulated combined some Lagrangian tracking also with the sheet breakup model to simulate the behavior of a large number of droplets. I mean, the number of droplets that has been studied is sufficiently large so that it is statistically meaningful to get a droplet size distribution directly from the simulation. So that can be a very comprehensive kind of model, but both this DNS and this model, this kind of model, as also the next that I am going to show, these are computationally quite intensive, and certainly at the present level of computational resources not suited as design tools, but they can definitely enhance our understanding about the nature of sprays. There has also been a multi-scale approach in which Lagrangian droplet tracking has been combined with volume of fluid method, and that also gives you directly the droplet size distribution at different regions of the spray. The author of one of the authors of the paper, Dr. Gaurav Tomar, he is also here. So this is at the present status of the second part of the submodule, that is the droplet breakup module. Coming to the third part, which is the droplet size and velocity distribution. As I mentioned, this is the stochastic part of the comprehensive model. It tries to model the uncertainties that are built into the atomization process. The two commonly used approaches are the maximum entropy formulation and the discrete probability formulation. Although there have been some work like one by Dr. Tarakan and Dr. Ramurthy, which made a very intuitive use of the linear stability growth rates to predict droplet size distribution. But mostly the prediction of droplet size and velocity distribution is done using this maximum entropy formulation, where the distribution function that maximizes the information entropy subject to certain constraints is taken as the most likely distribution. But there are several variants of the maximum entropy formulation that are available. One is how to define the distribution function. It could be number based or volume based. Then the statistical approach that will be followed, and the constraint conditions. What are the constraint conditions to be used? My colleague Professor Amitava Datta, he has detailed these issues in the book of abstract. So there has been some work where both this MEF, this maximum entropy model, has been coupled with both linear stability analysis and nonlinear stability analysis to produce, and there has been good to reasonable amount of agreement. But considering the complexity of the atomization process, even what appears to be not so good an agreement is actually should be quite acceptable. But as I mentioned, in this part also there are several open issues, like what kind of statistical approach to follow. Original work, the initial workers, they use this Shannon entropy approach, but nowadays people are using the Bayesian approach. The advantage of Bayesian approach, the disadvantage of the Bayesian approach is that it requires an a priori specification of the probability distribution function, but it facilitates a much easier conversion between volume based and number based PDF. Then what kind of constraint conditions are to use? Generally people use the constraint conditions which are based on the conservation equations, but they in a mathematical sense they imply constraining on the basis of higher moments. There have been certain alternative approaches which stresses that the constraints should be based on the lowest moments. So that is also again an open issue, and again a very important issue is that if you follow this conservation approach, conservation equation approach, then how to write the energy equation. Normally what is done, the liquid sheet kinetic energy and surface energy, they are balanced, but there is a school of thought which says that the internal energy, inclusion of internal energy can also be significant, but its impact on the ultimate spray distribution, the size and velocity distribution, that has not yet been by Professor Sujit's group, where spray characterization has been done making use of a wide range of available optical techniques like spray cone angles using Mie scattering, liquid volume fraction using laser induced fluorescence, finding the droplet size distribution and the mean diameters from PDPA, and using LDV for getting the droplet velocity field. So I mean, I just mentioned this, I could not elaborate on this. So to sum up, this is well known that spray characteristics are crucial to performance of gas turbine combustor, and conflicting requirements of spray characteristics lead to design of advanced injectors. For these design processes, comprehensive models can be very helpful, but in the to develop the comprehensive model, there are several issues which are not yet satisfactorily resolved. Both advanced visualization techniques and advanced computational techniques can facilitate resolution of these issues. Thank you.
So thank you, Professor Mukhopadhyay. So we have time to ask 2-3 questions.
Following the various methods that you mentioned for predicting droplet size and probably velocity distributions.
Right.
Have these methods been applied to acoustically forced sprays?
I have not seen these methods applied to acoustically forced sprays. But do you foresee any special difficulty in that?
No, I just wanted to know if it had been done.
For gas turbine combustors, but of late we are going to very high pressure ratios. So, in your, in the review that you've been doing, have you ever looked at high pressure supercritical sprays, and what should be the method and strategies for modeling them? Have you looked at some of those?
No, in this review I have not looked at. So,
thank you. So,
I have sort of a comment to make here. When you talked about various methods of simulating atomization, liquid sheet atomization, I think you based on one of the methods which actually is, Professor Herman is here, and closer, okay. This method actually involves what they do is they look at the primary atomization, they model the primary atomization by interface capturing proper full scale simulations. But when you get the PDF distribution of the sizes, then you use a Lagrangian spray model which have been well established for the secondary atomization. So in our method that you talked about, that is missing. So what we have is we get the droplets, but then we advect that droplets. We don't have the secondary breakup, which can be simulated using Lagrangian spray models. I think Professor Herman is better equipped to can elaborate on it a bit if he wants to.
What's the question?
The question is that the way we model, actually probably we could also save this question for the discussion tomorrow. But my comment is that that there are various models, but then like the way you used the Lagrange spray model for the droplets that you predicted from primary atomization. That's one way of it. But what you're missing in that is probably the interaction of the primary droplets with the jet, the downstream jet.
That's true to an extent, unless you, as you do and as we do in some cases as well, transfer them back into the tracked representation. And the underlying idea is that you get those interactions in a tracked, supposedly fully resolved type of DNS type simulation, and then only deal with the far field spray dynamics in a secondary atomization Lagrangian type way. And I agree that has to be taken into account. This two-way coupling interaction again of going back from a Lagrangian to a
continuum.
Yeah, I agree.
So probably we can save this comment to have a long discussion tomorrow. I'm hoping.
Agree. Yeah, we can have long discussions.
Yes, actually, I mean, secondary atomization is, I mean, all the modeling approach. I mean, I should have mentioned probably that it's mostly limited to primary atomization. Secondary atomization is still treated mostly in a somewhat ad hoc manner. I mean, there has been some studies like you mentioned, but mostly they have been based on like this. If you look at this this work by the Purdue group, the Professor Hester's group, they use a very detailed primary atomization model. For the secondary atomization model, they use the Ponstein's correlations and some modifications of Ponstein's correlation, that kind of thing. So secondary atomization is definitely a very gray, or maybe even more towards the black area, not even gray.
Just want to respond to Santosh's question. We had done some measurements on what happens to a spray when there is acoustic oscillations, and in fact, it affects the atomization quite a serious way. But I know about some modeling efforts in TU Munich with Patrick Demps and Polifke, but I don't think they're done with the study, but they're trying to use our data. But I think this is something which needs serious investigation, I think, with CFD.
So, well, if there are no further questions, let's thank the speaker, Professor Achintya Mukhopadhyay, once again.